So this topic is about an implementation of OST pools we have in production to limit the impact of such painful failures that cause downtime on the file system and sometimes result in data loss. So first we have to be prepared for failures. As the compute power of clusters is increasing, we have larger and larger storage system with more and more components. So Lustre is very good to make this scale and to ease us to aggregate all these resources to increase the bandwidth and the overall performance of the file system. But of course, as the mean time between failure of components remains almost the same, the more components we have, the likely there is some failure somewhere in the system. The chart here is a modeling that has been done by Oak Ridge about the average mean time between failure of large MPI jobs given the node mean time between failure. So of course this modeling shows that the larger number of nodes involved in the computation, the higher the failure probability and the lower the uptime. So I guess we could do the same thing for Lustre file system with all its OSS. The more OSS, the lower the mean time between failures. So at the end, with large-scale systems, the failure becomes the norm. There is always somewhere a component which is failed, and everyone as storage architects, storage file system developers, and system administrators have to be aware of that and deal with that to ensure the system availability. A corollary of that is if your monitoring is all green, maybe there is something wrong with your monitoring on large systems. So these are the common ways we most use to prevent all these failures. Red protects us against silent corruption, block corruption. It protects about a reasonable amount of these failures. There are also dual attachment technologies with multipass to prevent to protect against damaged fiber channel links or controller failure. And on top of that, there is high availability with a pacemaker to deal with server failures, network adapter failures, or even software failure like LBug. But when I could have a file level replication that will help with that. But beyond this, when larger failure occur, then you go into big troubles. If you lose more this than the parity, it's a very bad situation. Or if you lose a whole disk array due to a double crash controller, or even if the HA fails to fail over the resources, this can also generate downtimes on the file system. And striping makes it worse because by default Lustre tries to maximize the bandwidth, so it tries to load balance the load of the system. So when a user in a computation writes many files, likely its files are spread everywhere on the OSTs. So if we lose an OST, likely every dataset, every user dataset has at least one piece of data on the failed OST. And at the end, every user, every computation is impacted by such failure because often a partial data set is not usable. If somebody computes, I don't know, a climate simulation, if it misses one country, he can't resume his simulation. If you make a crash test and you miss the driver sensor, your result is useless. So often partial data sets are not usable. So even if you lose one stripe of a data set, it's no longer usable. So the idea is to groups user data or computation data into failure domains. So basically, a failure domain can be a HA cell. So if we do so, like in this example, we group every stripes of one data set on a pool of OSTs and other stripe on another pool. If a failure occurs, of course, some datasets will be even more partial or totally unavailable. But here in this example, there are 2 failure domains. But if you have 10 failure domains, if you imagine 10 failure domains here, only 1/10 of the datasets will be unavailable, and most of the data remains fully available. So to group stripes, there is this feature in Lustre, which is here since 1.8, OST pools that allow to define logical groups of arbitrary groups of OSTs. So this is a little how to create a new pool with pool new, pool add to add OSTs to the new defined pools. And then you can assign files to these pools explicitly using setStripe, but also by assigning a pool to a directory. Every new file or subdirectory created under it will inherit from this pool. So when you create a new directory to run a computation, if you use this this pool assignment, all data under this directory will be located in your failure domain. Then, what's the right size of datasets? For example, we could imagine grouping all stripes of a given file on a particular failure domain, but likely a given computation consists of many files, so even if all your stripes of a given file are available, the data set is larger than this, and it will be still be partial. Another idea could be to group user data per failure domain. So in case of an OST failure, some users will not be impacted at all. Most users won't be impacted at all, but the impacted users will have no data available at all, so they can work. Even worse, if you group your data into pools per group or community, if you have an OST failure, the whole community won't be able to work. Whole communities will be totally impacted and won't be able to continue their job. So the granularity we choose is to group per study or per compute job. So in this case, when there is an OST failure, some job data will be unavailable, but as user in general run multiple computation at once, every user will still have safe data set to work on, and so it's not So it can still work even if some of these computations are no longer available. So what we want also, I'm just stepping back one. So we want to have the user data spread across the multiple pools. So every user has jobs that can still be accessed, job data that can still be accessed. So what we want is to create one job on one pool, create another job on another pool, and so on. So one possible solution for that is to make the user explicitly specify a random or round-robin pool when it creates his job directory. Or, so this avoids putting all users' eggs in one single basket. Another solution is if the directory tree of the users allows to determine what directories consists of what job, like in this example. If we change at regular interval the pool assigned to this directory, then every job the user will start will inherit from that pool for the given period of time. Then if we reassign every hour or every 6 hours the pool assigned to this directory, without the users has to do anything, it will have its jobs created into the multiple pools. It will do a round robin of its data location. As a bonus, if you use this method, you can stop assigning user directory to a pool where there was a failure. So if you have a failed OST, you stop assigning the related pool to user directories, and all the new jobs will be created to sane pools, and the production can still continue while your OST is unavailable. But it could also be used for other situations, not only failures. For example, if you have a big red rebuild to lead on some OSTs, you could wish to offload this OST while it is rebuilt. So you can also use this pool mechanism to stop IOs, all new IOs to this pool while to speed up the rebuild. One drawback of this method is that you should say one job cannot use the whole file system bandwidth at once. As we restrict him to a limited set of OSTs, the bandwidth of the job is limited to this bandwidth. So it's okay if the compute cluster is full or small or medium jobs, but if you run big computation taking the whole cluster, which I guess is not the most common use case, then this method has drawbacks. So what you can do to adapt this method is to define larger failure domains, for example, for using 2 HSL for medium size computation, or more for large job, but keeping the same idea of partitioning the file system into multiple pools. So this is the first part that describing the solution we implemented. So if you like this method, you may want to do the same thing with your existing file system, with your data which is randomly spread across all OSTs. So this is something we did when we set up this pool partitioning. We had existing file system with many data in it. So this is what we did to reorganize the existing data. So we used Robinhood. So in V3, you can easily do this just by configuration. We declared no pool file class to match all files that had no pool assigned to it. And then we define a custom policy, move to pool, to be run on each pool, on each file having no pool. So here we have defined a basic status manager just to keep track of OK failed status of the command, to track the progress of the pool assignation, and to keep track of errors in case of the pool movement. And we define here an action which is calling a custom script that will select a pool for this file and trigger and run an LFS migrate command. So you can use LFS migrate -p pool for assigning, for moving file data from its current location to a given pool. Notice that LFS migrate since Lustre 2.8 is more safer. Previously, it used a group lock to prevent from user accesses during the migration, which forbid any access to the file while the copy was down. And moreover, it was racy. You had a race between releasing the group lock and switching the layout, which was racy. So it was fixed in 2.8. Now a user can access the file while there is LFS migrate. This will cancel the migrate, but it will be access safe. And it's raceless, so if the migration is okay, you have no risk of losing data or changing. And so finally, it's just saying that we want to run the move to pool policy on this no pool file class for files that have not been recently accessed. So this job does the job of migrating our files. So this is the simple example. Below, I put a more enhanced case with two sub-rules. The idea here is that if you want to LFS migrate small files, you can do it locally on the Robinhood node where Robinhood is running, because it's not worthwhile paying the price of remote communication to do the LFS migrate remotely. So this is what is said here. No pool, we call the migrate local script. And for larger files, it may be good to distribute the LFS migrate operation on multiple nodes to maximize the bandwidth. So in this case, for larger files, we call a migrate remote script that basically could do SSH some node and LFS migrate. So this allows running this operation faster. So this is just an illustration of the progress. You can, during this operation, you can see how much files are still not assigned to any pool. And you can ask the status for this move to pool operation. You can see how LFS migrate succeeded and or failed. So this gives a good tracking of the operation. So as a conclusion, even if RAID and high availability, bad things can occur on the file system. So we are happy with this method we implemented. It gives good results when we have an OST failure. It was the first time we used this pool this pool feature in production for all files such massively. And we are very happy with the stability of this feature, and it met our expectations. This is also an example of using Robinhood for pool-to-pool migration. It's interesting that we have perspective to use such policies for migrating data. So in this example, we moved a file from no pool to another pool, but we could imagine applying this for moving from SSD pool to hard drive disk pool. And of course, there are even more perspectives with FLR and progressive file layer. That's all. Any question?
Have you looked at any integration with job schedulers for this idea with pools, like scheduling jobs into specific pools? Or just Robinhood is the main engine of doing the work?
Sorry, can you? I didn't.
Sorry, did you do any looking at integration of this with job schedulers to schedule jobs directly into pools, or is the Robinhood the main policy engine for this?
None of these actually. We just run a script hourly that goes through every user directory and assign it a pool. So every new job coming and creating a new directory in this under the user directory will inherit from this pool. So by running this regularly, new jobs go into different pools. There's a round-robin mechanism on the job location.
Okay.
Here, Robinhood just schedule the action of LFS migrate for the data that existed before this mechanism was in place.
Okay. So if I had one job that ran into, let's say, pool 1, and so my next job may so if the script ran, it changed striping from my folder to a different pool. So basically my second job can end up in a completely different pool.
Yes,
that's how it works.
But your existing, your first job will still remain on the
previous pool.
On the previous pool, yeah. Because
is there a risk that I have a job that started before the script ran and changed the pool? So I have some data on previous pool for the job and some data on another pool?
No, because the directory inheritance is only done at creation. So once you have created your job directory...
I see, so each job will have its own folder, basically. That's how it works, okay. So it requires users to be very... they need to basically be very organized.
Yes.
Which they aren't.
So to determine the right place in the namespace hierarchy to set this pool, so you can start from the user directory, or sometimes you can start by the lower level of the tree and see where are the files created by users. So it needs to look at precisely how they organize their data. But as I said, the other solution is to make user run a particular LFS set stripe command when they start a pool, or you can provide them, or maybe in the integrate this to a scheduler prog of the scheduler to create the job directory.
I thought it was just worth mentioning, you're saying using the OST pools to offload from a RAID rebuild, right? To reduce the IO load there. There's actually a functionality on each OST. There's a proc file, you can say degraded. And so if you're doing a RAID rebuild, you just echo 1 into the degraded, and then that gets sent to the MDS on every statfs. And actually in Lustre 2.10, if you do LFS-DF, it actually shows those states now at the end of the DF output. And so the MDS will skip that OST for new object allocations, right? So you can do that on a per OST basis. I think that's existed for many versions already. And only if users stripe over all the OSTs would they use that particular OST again.
Yeah, that's true. And so another thing we do is disabling this OST on the MDS.
Yeah, yeah, but this is instead of disabling it completely, right? You can just flag it as degraded so that it's just less preferred, right? But it's still usable if needed.
Thank you for the tip.
Andreas, do you know in which version of Lustre this was integrated?
2.11.
11.
2.3 or something.
Okay.
So in 2.10 it's only the output in DF common that it's new. Okay.
But the problem is, if an OST is damaged, you cannot read from it. So if your data is still there, already there, then this helps, I believe.
I mean, this is definitely a good idea from the fault tolerance point of view and everything. I was just saying for the RAID, reducing the load on a particular OST for a short time. And actually, one of the things I didn't mention for ZFS, there's a Z script that if the ZFS is rebuilding, it will automatically set the degraded state on the OST so that it will get faster rebuilds because it doesn't have the write traffic. It'll still do read traffic because you can't not read from the OST, but something for LDiskFS. The problem with LDiskFS is that it doesn't know, whether how the hardware RAID is rebuilding, right?
Mm-hmm.
So you need to have something that's specific to your hardware, or administrative command. But for ZFS, it knows that.
Other question? Okay, thank you, Thomas.